welcome to this presentation. This is Sadeep Nanda here from NIT Rourkela. Today we'll be solving a numerical from the book Engineering Dynamics authored by Meriam and Kraige. The numerical is a part of the chapter Plane Kinetics of Rigid Bodies. The allotted numerical is number 58. So here goes the numerical. A uniform cylinder bar of mass m and length 2b is mounted in a right angle frame of negligible mass. So this is a right angle frame and the subjected bar is of mass m and length 2b. This is pivoted to the point O. The bar and frame rotate in vertical plane about a fixed axis at O. The bar is released from the rest in the vertical position theta equals to 0. Derive an expression for the magnitude of the force exerted by the bearing at O on the frame as a function of theta. So in this problem, basically we need to find the net hinge force acting on this entire system. The very first typical highlight of this problem is alpha, unlike other simple rotational problems, here is not constant. Alpha changes with the angle theta. As we know that net torque applied at a point is equal to the product of moment of inertia of the body at the point into its angular acceleration, which is tau equals to I alpha. So we found tau here, that is the total moment, total torque acting at point O to be mgb cos theta, and it equals to I alpha, where I is the moment of inertia of the rod about O. The moment of inertia, as we have found it here, is 4 by 3 mb square. After solving this, we get an expression of alpha which comes out to be 3g cos theta by 4b. Here, as I said, alpha is not constant. So alpha changes with the angle theta. So does omega. Omega stands out to be the angular velocity, and we need omega to find the centripetal force acting at the center of gravity of the mass. So we know the equation omega d omega by d theta equals to alpha. We simplified the equation here and we integrated it up to 0 to omega on the left hand side, and on the right hand side we integrated it from putting the limits from 0 to theta. What we ended up with is omega square equals to 3g sin theta by 2b. This omega square will be used in the further part of the problem to find the centripetal acceleration. Now, as we can see here, at this point, at the center of gravity, we have an outward force, that is m omega square r, where r is nothing but b, that is the distance between the center of gravity and the hinge point. We need to find the normal component of the hinge force that will be acting on this whole setup. The normal component here is equal to m omega square b, that is the centrifugal force, plus the component of mg in the component mg sin theta. The summation comes out to be 5 by 2 mg sin theta. Now we need to find the tangential component. As we know, the tangential velocity when the body is in a circular motion is equal to the net force acting on it at that point in a tangential way. Here the total tangential force that will be acting will be equal to the mg cos theta minus the 3 mg cos theta by 4, which happens to be the value of m alpha r, that is the angular acceleration. So the tangential component will be mg cos theta by 4. The last part, a very simple one, That is, we need to find the net force applied on the frame by the bearing at O, which happens to be nothing but the resultant of both the components, the normal and the tangential components, squared up under a root over, which comes out to be mg by 4 root over 100 sine square theta plus cos square theta.